Sure.
So, my pleasure to introduce Professor Kathryn Mann from Brown University. She gave a colloquium talk yesterday, and from today, for 3 days until next Tuesday, there will be briefing courses and group actions and low dimensions. So, please welcome Professor Mann.
Thank you. That's great. Thanks very much. I'm excited to have lots of opportunity to talk about mathematics. This will be related to the topic that I talked about in the colloquium, but we're going to approach kind of problems there with completely different methods. It's also related to the talk I gave at the conference at SKKU, which grew, that problem we solved grew out of some of the work that I'm going to explain here. So I put up some general references. The first 2 papers, this paper of Etienne Gis called Groups Acting on the Circle is a wonderful place to start accessing this subject. It's beautifully written, and there's lots of ideas from different areas of maths that converge there. At some point I was asked to write a survey paper, so I tried to write kind of a sequel to this, talking about sort of areas that were left out and new developments since then. And by the end of this mini course, I want to prove a theorem, or a special case of a theorem that I proved with Maxime Wolf, not the one that I talked about previously. So this paper we wrote kind of as an expository version of a special case of a very hard theorem, because this one's the type of, this sort of captures the essence of the idea in a way that's readable and friendly, and that I'll try and explain by the end of this course. So that's just sort of some general reference point if you end up looking into this further. Let me tell you the plan for the next 3 lectures. Today we'll do, let me move this so it's not in the way of the board. Today I want to talk about and introduce some classical tools and things that have come up in previous things I've talked about, but we'll actually go slowly and work through definitions. Some of the motivation for this work and the basic objects. I'll talk about foliated bundles, the Milner-Wood inequality, the Euler class, and rotation numbers. So these are classical tools and classical objects. On Monday, I want to talk about some work of Bill Goldman that was really the inspiration for me to get into this subject. And kind of paint you a picture of a comparison of representations into PSL2R, a Lie group, a nice thing we like to study in hyperbolic geometry versus this much bigger group. This is acts on the circle by Mobius transformations, but it sits inside this much bigger group of homeomorphisms of the circle. Okay. And this is all to kind of introduce kind of spaces of bundles or spaces of group actions. And then on the last lecture, with all of this background, I want to prove the main theorem, the one from this version of our work here. Okay, and hopefully by the end this will paint kind of a nice cohesive picture. Oh, and I guess I should along the way I'll try and mention some directions for study, some accessible points, some open questions. Hopefully I'll, if I don't do enough of that along the way, I'll make some time at the end to introduce next questions. Okay. So that's our plan. Each one of these will be quasi-independent, but use, I'll try and frame them enough so that, we can kind of start and it's a complete picture at each lecture, but I'll use, definitions from previous ones in the next ones. So they're structured in this order for a reason. Okay. So that's our plan. Let's get started. I want to talk about some beautiful and classical objects and how we think about them. And I'm actually going to set things up so that we can prove a famous theorem, the Milner inequality. Set up correctly, we should be able to prove this quite quickly at the end. Okay, so starting off, let's talk about topological fiber bundles. This is going to start by sounding like a topology lecture. Actually, all my fiber bundles are going to be very special. I want the fiber to be the circle, so these will be topological circle bundles. Let me remind you of the definition, what I mean by this. Circle bundle, I think a lot of people are familiar working with vector bundles or something, but that's topological fiber bundles are the case I want to work with. A circle bundle over a manifold M is a space E and a map, a surjection P from E to M. Okay, so that the fibers of this map, the point pre-images, so with the pre-image of every point, a circle, and satisfying a kind of local product condition, okay, such that for any point in your manifold, there is a neighborhood U of X, so that if I look at the pre-image of it under my projection map, my map P, okay, this is homeomorphic to U cross the fiber S1, and this map P under this identification is just like projection onto the first coordinate. So this means it just looks locally like a product, but it could be globally not like a product at all. Okay, so example, okay, I guess example 0 is literally a product. Okay, that's not a very interesting example. But here's another natural construction. If M is a Romanian manifold, Okay, so it has a Romanian metric. In particular, you can talk about its tangent bundle or tangent space. Then at every point, I can look at the circle of unit well, let's do a Romanian surface, a surface with a Romanian metric. Otherwise, I'll get sphere bundles. So surface with a Romanian metric. Okay. So you can even think of it as physically embedded in 3 space, and now you can actually talk about tangent vectors. UTM is the unit length tangent vectors at any point. And if you forget what the vector is and just the point it's attached to, that gives you a map back down to your manifold. And the fiber of this, well, it's just the unit tangent vectors at that point. That's a circle. Okay, so that's a natural construction. Here's another way to get a huge family of examples. Okay, this works for any manifold. So given some manifold M, you can take any homomorphism from the fundamental group of your manifold, okay, to the group of homeomorphisms of the circle. Okay. And to save ourselves headache, I really prefer things to have orientations. I don't really like non-orientable manifolds. So I'm going to make this go to the group of orientation preserving homeomorphisms of the circle, although it's not strictly completely important. This will just make our life easier. Okay, so I have a homomorphism from this group to this group, and now I can make the following construction. I'll take M, I'll look at its universal cover. I'll take the product of the universal cover with the circle. So now this is a product bundle, but it's not exactly example 0. I took the universal cover. And now I'm going to make an identification. I want a pair of points to be identified with another pair of points. So X in the universal cover, comma, I don't know, S in the circle, will be identified by, if I act by an element of the deck group, the fundamental group. Okay. I'll glue these points together if the S coordinate differed by the action of rho. Okay. So I make this identification for every element of the fundamental group. Okay. So schematically, a picture, I don't know, maybe M is like a 2-dimensional torus. So its universal cover is R2, the plane. Okay, I'll draw it kind of slantily. So you're imagining this is like the XY plane in 3 space. And what I'm doing here, so forget, this is just the universal cover map for the moment. I've taken R2, I'm going to cross it take a product with a circle. So I'll draw the circles in this direction, except I'm going to draw them as lines. I don't know, pretend this point is identified with that point. So it's really a circle over every point. Okay, that's this space. And now I don't want this, I want a quotient of it, where I'll look at a fundamental domain here. There's an element of my fundamental group that translates this over 1. Okay, so I want to glue this square to this square, but actually I've got a square across a circle worth of things. I'm going to glue this circle to this one unit over, by whatever this element of the fundamental group is supposed to do to a circle. Okay, that's specified by this map. Okay, so I'm supposed to glue fibers to fibers. Okay, so this builds me some kind of space, and if I forget what circle I'm in and just what point I'm attached to, okay, there's a surjection back down to M. So now this is the picture that I've drawn. Every every one of there's exactly one fundamental domain worth of circles left. And so if I just remember the point you're attached to, you go back down to the torus. And the fiber of each of these maps is one of the circles that was originally attached. Okay. So this is a recipe for building tons and tons of examples as from just a purely kind of group theoretic construction. Cool.
If you
Questions?
trivial action, you go back to 0.
Yeah. So in particular, if you take the trivial action, you get this one. Okay. It is maybe unclear whether there's something you can do to get this one. That's a good thing to think about. We'll get there eventually. Whether there is or whether there's not. Maybe let me give you another concrete example. Perhaps I should have done this before I gave you like an infinite family of examples. Here's another example. I like the torus there. So let me give you another concrete example. This one's called the Heisenberg manifold. Okay. So what is this by definition? The three-dimensional Heisenberg group, the three-dimensional real Heisenberg group, is by definition, this is going to be the building block in here, upper triangular matrices of the form, with ones on the diagonal. So I'll put the other entries, they can be whatever real numbers you want. Let's call it x, z, and y. Okay, so that is just as an abstract space. I've got 3 real coordinates. I can think of this as being R3 as a space. Okay. Okay. So here x, y, and z are just real numbers. Okay. Its integer points. It's the same thing, but you require the entries to be integers. Okay, so this is obviously, if you think of this as a matrix group with multiplication, this is a subgroup of there. And I can form the quotient just look at the space of cosets. Okay. And this is just some topological space. And as a nice exercise, you can check that this has a surjective map to a torus, a two-dimensional torus, okay, with fiber the circle. And in fact, there's a really nice way to think of this as a topological space. It ends up being, you can do this by taking like a unit length cube, if you like. Okay. And if I was going to build a three-dimensional torus, I should identify the opposite faces in pairs by a translation. Okay. To build this space, left multiplication in this group is not the same as in R3. So I won't identify these just by multiplication. You should identify, just by translation. Identify the front and back and left and right sides in the usual way, say. Sides of this just by translating over. Okay, but top and bottom, by a map that takes, this square to something that's sheared like this. Okay, so by a linear map that looks like, say, 1, 1, 0, 1. Okay, so if you do that between this square and this square, you'll do a shear. Okay, so that just builds you a space, and it's from this description, it's not so hard to see where the torus is sitting in here and what direction the fibers are. Okay. So this is a nice thing to kind of work out on your own as a little puzzle in topology. Okay, so here are some concrete examples, and a question you can just ask is, a very natural question. I gave you specific, and specific things, and then a general construction. Can this general construction produce all of these specific examples? Here's a fundamental basic question. Which examples of circle bundles, so we usually write this as S1 Romanian, so that's the fiber, of topological circle bundles can be attained by construction. What number was this? 2. Okay. This one, yes. This one, I don't know, maybe it depends on the surface. Okay. This one, well, it either can or it can't. You can play around and maybe you tell me, maybe someone will figure it out by the end of the talk, or we'll have to come up with a method of it. You know, it's not just like, we'll need some kind of invariant or something to tell us whether it can or it can't. Maybe everything can. This seems like a pretty general recipe. Okay, so our next goal is to answer this question. We're going to answer this question in the special case where M is a surface. It's two-dimensional, so a surface. I guess a closed surface. And the answer is a famous theorem, which we'll end up proving. Okay. But to do that, I should introduce us to some tools. And this tool is the Euler class for circle bundles, which is something that I hinted at, but I gave kind of a funny definition in a previous talk. So let's do this correctly the right way. Okay. Okay. So here is a tiny bit of algebraic topology for the day, or classical topology. I won't get too crazy with algebraic topology. Okay, so the Euler class of such a construction of a S1 bundle over a manifold let's stick to surfaces because that's what I'm focusing on, but it'll be completely general. There's a reasonable way to generalize this definition, which should be apparent by the end. The Euler class of this is an element. Okay, so given the data of a topological circle bundle over a surface, you have some three-dimensional manifold with some extra structure. It's an element of the second cohomology group of your surface. I'll use integer coefficients. And it measures what we call the abstraction to a section. So what's a section? I have a map here in my definition, P from E to the base, which here is a circle. A section is an inverse, in some sense, to P. So a section is a map S. It's a continuous map S from your surface into the bundle. Okay, so that S composed with P is the identity on the surface. So that S composed with P is the identity. Okay, so it's a way to embed this up here so that it projects back down to where it's supposed to be. Okay, so for example, this definitely has a section because I can just, if I have M cross S1 and I project down to M, I can embed M back in here as M cross a point. Okay, great. So trivial bundles always have sections. This one, if your surface is not the torus, this one definitely does not. Right? Actually, this is a theorem that we learn about, like the sphere. This is the hairy ball theorem, right? You can't pick a unit vector at every point on the sphere in a continuous way. Okay. And in general, right, this is, we think of, for the unit tangent bundle, the abstraction to picking a unit tangent vector actually comes from the Euler characteristic of the surface. Okay, but let's not get too ahead of ourselves. We want to define some 2 cocycle that measures, well, if it's 0, I want it to be 0 exactly when you have a section, and non-zero if you fail to have one. So here's a concrete construction. Let's do this where I actually have space. So there's an abstract way you can do this. Let me do it in a very concrete way instead. If you say triangulate or take a cellular decomposition, decomposition of your surface, okay, then I'm just going to try one skeleton at a time to define my section. So here's a surface, okay, and I've, I don't know, got some 0 cells and some 1 cells, and I don't know how it goes on forever. I get tired of drawing it. I at least have 1 2 cell in there, and who knows what else is there. Got a nice triangulation, and above every point I have a circle fiber, right? But this is really a whole cylinder over this 2 cell cylinder. I've attached a circle at every point. Okay. So let's just make arbitrary choices and try and define a section. So we'll define S arbitrarily over the 0 skeleton. So for each point, I'm just going to pick a point in the fiber above it. Okay, some points so that when you project back down, you get right here. Okay, choose whatever you want. Okay, I had another 0 cell over there. I'll pick a point. Okay. Once I've done this, I can extend it to a continuous map over the 1 skeleton, right? Over any edge here of a triangle, I see a cylinder, a circle cross edge. Okay, and the circle's connected. I can just go from this point to that point as I go along the cell. So extend over one skeleton? Yeah.
Maybe there are infinitely many choices.
Yep.
In this step, we do also arbitrary.
Yep, arbitrarily, right. Yeah, I could go around here 5 times if you wanted to. Whoop. Here, I'll draw a crazy picture. And here, I'll take the short route. Do as you please. Okay. So again, arbitrarily. You're probably thinking, how are we going to get a concrete definition with so many choices? Okay. But now, whenever I have a 2-cell, so I've got this one triangle that I've drawn in here. Okay. The question is, can I extend this over the boundary, over the interior of the 2-cell? Okay, so let me draw this picture just sitting on its own. I have this triangle. This is my 2-cell. And instead of circles, I'm going to draw straight lines because that'll be easier to draw. Okay. Okay. And of course, if my section that I chose arbitrarily was something like this, and then across the back like this, of course I can fill this into a continuous map, right? But if I did something like this instead, where I go up at the edge, and then here, it's not quite so clear what can happen. Can I do this one? Can I fill it in? No. Okay, what's the obstruction? Yeah, I've gone around or something like this. Okay, so what's actually going on here? So for a 2-cell C, I can think of the boundary of this as a circle. Okay. And to each point in this, I picked a point on this circle fiber, right? Really, my boundary is a circle, and I see here a circle cross a circle worth of fibers. Okay. So my section that I've defined so far, S restricted to the boundary, gives a map from the circle to the circle, the fiber circle. Okay. So this guy is the fiber, and this is a continuous map. I mean, injective map even. No, it's just a continuous map. Okay. Okay, to every point here, I've picked the point in the circle. Okay. And so I can look at the degree of this map. And if the degree is 0, this is exactly what it means to be able to level it off. And here I had a degree 1 map. I went around once, and you can't. And the degree, the number of times you wind around, is exactly measuring how far away you are from being able to just glue in a 2-cell here. Okay. I guess, yeah, here my degree is 1, and the flat one is degree 0. That's exactly what it means, is I can cone it off. I can sort of level it off. Okay. So the degree, let's get some more space. The degree of the restriction of my section, as I've defined it so far, is some integer. And it's 0 if and only if we can extend S over the 2-cell. Okay. Being able to extend this over really is producing a homotopy of this map with a constant map. Okay. Okay, so what's the upshot here? Okay, this gives an assignment from 2 cells and my surface to integers. Okay. Okay, that depended on tons and tons and tons of choices, but if I think of its class in second cohomology, this turns out to be actually independent of the choices. So I did this for a fixed triangulation, right? And you might want to be like using some simplicial homology where you just don't have a fixed cellular decomposition. But you can prove, if you have different ones and you subdivide, it behaves nicely. This gives you a well-defined map in general. Okay. And like every time you have to check that something's independent of a billion choices, it takes time and several boards. But there's no magic. You just check what happens if you make one different choice at a time. You've changed something over the one skeleton. Really, you have to check if I change one edge by winding around one more time, that this differs by a co-boundary in here. Okay. Okay. That is the Euler class. Okay, so more fun than checking that this is independent of all the choices you made. You can try and compute or describe what this is for, say, the Heisenberg manifold. Okay. Once you've kind of figured out the construction of this, its second cohomology of the torus is not hard to compute. And what this particular, well, we all know second cohomology of the torus. What this particular element is that comes from this bundle is something you can just describe completely by hand. Okay. And heck, you could do it for the unit tangent bundle of a surface also. It won't matter what metric you want to put on it also. Okay. Okay. Oh, and I guess I should say that, this winding number being 0 means you can extend the section you chose over a cell. The class being 0 means you can extend it generally, right? This is capturing exactly what we wanted. This class being 0 is 0 in second cohomology if and only if there is a section to the bundle. Okay. So i.e. here, it's 0 in H2 if and only if a section exists.
Professor,
Yeah.
This can be a silly question, but
Right.
I can expect the generalization for the base space. If
Yeah.
it becomes n manifold, we use n-1 homology class maybe, but I don't quite see the generalization of the fiber. If it becomes S2, is there any reasonable?
Yeah, so let me tell you the two ways to generalize it. So the base one, actually this is always going to be two cohomology class where you actually only look at two cells. Right? This gives you, if you take a surface inside of your bigger manifold, you can look at the restriction of your bundle to the surface, and this is already giving you information. So in general, this is a nice aside remark. Okay. So in general, if you have a sphere bundle, okay, same definition, but replace every one with an n. You have an n-sphere bundle over any manifold. This has an Euler class, which now lives in the n+1 cohomology of the base space with integer coefficients. Okay. So, and the definition is exactly the same. You triangulate your manifold, and you start trying to extend things here. Now, why could I not, I have a map of the boundary of a disk into the circle. Sometimes I can extend that, and sometimes I can't, because the circle's not two connected, so I can't always put a disk in when I have a circle in there. But if I had a two-sphere and I had a map of a circle into a two-sphere, I can always extend that to a map of a disk. Okay, so there's no problem if this was S2 to extending this over the 2 skeleton, but there will be a problem to extend it over the 3 skeleton, right? Depending on if I sort of cover a whole 2 sphere and there's nothing on the inside, I can't cover it up. So the degree of the map, degree over boundaries of n+1 cells, degree, I guess, of a attempt at a section, over boundaries of n+1 cells generalizes exactly and gives you an element of n plus first cohomology. If you've seen the Euler classes of vector bundles, this is a generalization of that definition. Where if you think of a vector bundle, that's like here the analog to a circle bundle is an R2 bundle. If you puncture R2 at the origin, vector bundles always have a 0 section, so I can puncture that out because that's cheating. And now I've got a plane attached to every point with a hole, which deformation retracts onto a circle. So topologically, I basically just stuck a circle to every point. Okay. And the vector bundle definition of Euler class, if you've seen it, actually agrees with this one if you view those as circles. All right. But I like this one because you're only doing topology. Like you're only doing like the homeomorphisms topology, like cut and paste and glue things together. Okay. Okay, so this brings me to the theorem that spawned a ton of interesting mathematics. This is the Milner-Wood inequality. And the Milner part comes from 1950 something. I'm going to say 56, but I might be 2 years off. I'll have to check. And Wood is from 1978. Okay, so Milner did this for a special case and Wood did the general one. But secretly, Wood's contribution was to realize that Milner, if you unpack it right, could have proved something stronger. And so Wood saw how to do this and did it. The Milner-Wood inequality is an answer to our question, a complete answer. Okay, and it states that, let me put it this way, if I have a circle bundle over a surface, okay, of an orientable surface of any genus, comes from our construction 2. Okay. If and only if this class, is one of a fixed finite number. Okay, so how am I supposed to tell you like what is a cohomology class? Well, I'm in second cohomology of a surface of the fundamental. Second cohomology of a surface, right? I should evaluate this on like the fundamental class. That will just give me a number. So if I take this Euler class and I pair it with the fundamental class of your surface, I'll get some number. And you come from this construction if and only if this number is bounded by the absolute value of the Euler characteristic of your surface. So my surface has genus G. This should be bounded by 2G minus 2. All right, so I'm going to actually, let me give you the answer key to this exercise. I still want you to do the exercise because it's a good practice getting used to this, but here's the answer key. For this one, you should get 1 or plus or minus 1, depending on which way you multiplied. So if you pair with the fundamental class, So this pairs with the fundamental class of the torus to give 1, or maybe minus 1, depending on how you orient things. And this one pairs to give negative 2g plus 2. Okay. So already, these kind of easy to describe examples, one of them could not have possibly been obtained from my general construction. Here the genus is 1, so 2g minus 2 is 0. That's definitely bigger than 0. And here I'm hitting 2g minus 2, an absolute value on the nose. Okay. Okay, but pretend I didn't tell you this answer. Okay, so I want to prove this, but before proving it, let me tell you why it's interesting. Why do people care about construction 2? I mean, it's always good when someone's like, oh, here's a recipe to build examples. If you know, do you get all possible examples in that way? Like, that's the first question you should ask. But things that come from this construction actually are very interesting to topologists and geometers generally. Let me do a little digression. Why is construction 2 interesting? Why were two famous mathematicians working on proving this result, right? Well, when you have a fiber bundle or a circle bundle, okay, this comes for free every point in your space E. Well, it's part of some circle, right? Every point in here has is part of some fiber. Okay, I could think of X as, you know, the pre-image. It sits inside the pre-image of some point Y from here, because this map was surjective. And so, in fact, it sits inside, well, this is just a circle. So it's like at every point in here is part of some circle. I have a preferred direction. If I'm oriented, I have a direction of like going counterclockwise around the circle. Okay. So it has a preferred direction attached to it. So at every point I have a way to go. The ones that come from construction 2 have a preferred transverse plane also. Okay, so this we often call the vertical direction. We think of this projection being like going downwards, and the fibers are pointing up down. Okay, so I have a preferred vertical direction. Construction 2 also has an idea of what it means to be horizontal. Okay. So let me remind you what it was. I was supposed to take the universal cover of my manifold. Here it's the surface. Take a product of this with a circle. So that's going to look like, you know, big plane. This guy, cross circle, circle attached to every point. Okay. And in this space, I have a notion of what it means to be like horizontal or transverse to this circle. Okay, it's like if I look like a piece of the surface cross a point. Okay, so I have an idea of what it means to be horizontal. Okay, so this was the beginning of this, but then I took a quotient, right? Modulo, I'm supposed to act by deck group, and then by some action. So this piece here gets glued to another piece over here, and I change these things. But this is coordinate-wise. So it preserves my notion of S1 direction and other direction. Okay. So I can remember if, you know, something was part of a plane here, it might get attached to a different plane, but the notion of direction gets preserved. Okay. So to finish my sentence, construction 2 gives at every point plane transverse to the S1 direction. Yeah?
When you say that each x has the preferred vertical direction, you mean
Yeah.
global assignment of those directions?
Sure. Yeah. To every point in here, it's part of some fiber. And I can say, like, proceed clockwise around the fiber. So that means to every point I have somewhere, I mean, it might vary as you move, but there's a canonical choice of go clockwise around the circle to each point.
So is it obvious that we can assign that globally and continuously?
That you can globally assign this continuously. Yeah, so you don't have like a unit direction, but if you have an orientation to your bundle, you can globally assign tangent to the fiber direction at least, right? So actually, let me so let's get a bit more space so I can draw a picture. Right, so I really have an E, I was calling it, to surface. Okay, and if I look at a point in here I was calling Y, I can look at its pre-image. This is a circle sitting inside of here. Right, and so this gives me, I can think of this space, right, whatever it is, it's a union of circles. Okay, I've drawn chunks of them, and the local triviality, or definition by those little charts to open set cross circle tells me that these vary in a continuous way, right? I'm not seeing some suddenly being butted up against that. Okay, so this says that if I take any point in here, I know which way is going in the circle that goes through that point. Yeah, and I'll never see like a point here and then suddenly one whose circle is supposed to be like that. Local triviality. Yeah.
I guess the question is like whether there's any circle on the base space where the fiber over that circle is a non-orientable case.
Yeah. So this is why in construction 2 I put like homeo plus S1, and generally there's an orientation condition that you can put on these that says yes, you should satisfy that. Okay, so in general maybe your direction should just be a line and without an orientation. Okay, but I'll consider orientable bundles, which are exactly the ones where if you go around, so the Mobius strip is an example where this fails. If you just take or I guess the Klein bottle is an example where this fails, where I take a bunch of circles and I'm going to glue this one to this one by a flip. Yeah. Okay. But I like my manifolds to be orientable, so this will never happen. Okay, great. Okay, but in general, there's no hope that you'll have a well-defined way to pick out a transverse direction at each point. And the fact that you do means actually exactly that you come from this construction. Okay, so these are the exact ones where you have a transverse direction. And in the language of differential geometry, this is equivalent to what's called a flat connection on your bundle. Okay. Or in the more topological language, this gives you, if you have continuously varying planes on a manifold, you can integrate them to get foliation. Here you actually kind of see the foliation coming here. Okay. So in fact, what you get here is a foliation transverse to the fibers. So people who study foliations on manifolds or codimension 1 foliations on 3 manifolds are already fascinating objects. This gives you a whole family of examples. Milner was interested in this from the differential geometry perspective, where you interpret this as saying there is a flat connection, whatever that means. Wood was interested in this from this more topological perspective of when you have a foliation transverse to the fibers. And that's kind of, I'm sort of a topologist at heart. That's why I think this is a fundamental and basic question too. Okay. Okay, we're at the 1 hour mark. Should we take like a quick break for people to stretch, or should I, before we prove this? Or I don't know what the custom is when you have a very long time and talk for a long time. I don't know. Sure. This is a natural point to pause. So maybe we'll pause for, I don't know, 5 minutes. You can have a coffee or something, and then we'll prove this. Yeah.
Starting at 3:05.